Thank you guys for having me. I spent about 10 years of my career as a consultant, as a structural engineer. Really wasn't ever quite satisfied with what I was doing. Most frustrating part for me was that I realized somewhere along the way that a consultant really its first priority was to meet their budget, not the project's budget, but their own budget, right? And this doesn't necessarily mean that you get the best designs out of your consultants. This means that you get a design that nobody will complain about as long as you meet your budget. So it was always frustrating for me because I always saw all these opportunities where we could be doing more, we could be doing better, we could be more efficient. And I finally, at some point, I said, you know what, I'm going to go into more of a construction, manufacturing kind of environment. And I jumped over to the precast industry. And it was a little scary because it was unknown, right? But I have just loved it. I've never looked back. For 15 years, I've been in precast, in manufacturing, and it's so rewarding and it's so fun because you actually control what you're building, and you can manipulate it, and you can optimize it, and you can productize it and bring it out to the market. So it's been a lot of fun. So anyway, that's a little bit about my background. And with that, I'm going to talk about this new product. We've been working on this for, I'd say I've probably been working on it for about 3 years. Like everything, it kind of starts as a side project, and then it evolves into a bigger side project. And then it finally takes over as your main project. But we've been working on this office building as a product, as a productized solution to delivering an office building to the market. And I'll talk a little bit about this whole process, how we started, how we took it through the various steps. Let me see. Okay, so just want to kind of agile construction product development. So it's fun because I've been interacting with Crom. We've been working together for several years now, and he opens my eyes to all these different ways of thinking, or these formal definitions for ways of thinking. It's been a lot of fun working with him and going through this process with him, and him coaching me along the way. We have all these various phases that we've been going through for this product development and product delivery. First is this concept phase where we're looking at the market, and we're trying to figure out how big it is, and what we can deliver, what it values, what kind of things are there. Then we go into this inception phase where it's really about soliciting market feedback. And it's interesting because I found that I needed a feedback loop in that, an iterative feedback loop as we were soliciting input from the market. And then as we went into the actual product development, we needed another feedback loop with our internal customers. So we have one feedback loop going with an external customer and a separate one going with our internal customer to make sure everybody's happy with where it's going. And then what I'm calling a release, we have releases to the market, and we also have releases internally, which is interesting because they're separate as well, right? The releases internally are more, as we get a chunk of work done and designed, we release it internally so that the internal stakeholders have that piece of work to add to their wealth of knowledge as we deliver these projects to the market. So starting out with this concept phase, I'm going to try to keep this really brief. There was a lot of work. This is a ton of time going into this, researching the market, trying to figure out what they wanted. At the time, I was working as a sales engineer, so I was working with the salesmen, going into meetings, and trying to sell custom precast jobs to whoever was buying. And through those interactions, I learned a lot. And so we started formally studying the market. We started sizing the market based on Dodge data. We partitioned it, really trying to understand. And this is a more recent view of the California office market, what I'm showing here, trying to understand how big the market is, how many office buildings are built in California, and where they're built in California. Because I didn't really think about it ahead of time, but then as you get into this, you go, wow, 95% of the buildings that are built in California, the substantial office buildings, are built in one of 4 markets, and they're listed here: Bay Area, Los Angeles, Sacramento, and San Diego. And then there's a few just sprinkled in between that are in random places. And it's hard to predict where those show up. But it became pretty amazing. It's actually pretty easy to think about it that way. And then you start thinking about how well you compete in each of these markets, and you can really zero in on where you want to target. The other part of this is just understanding what's being built in the market. So looking at building height, for example, 75% of the buildings, or roughly 2/3 or 3/4 of them are built are under 10 stories in a category. They're actually under 7 or 8 stories. But knowing that a majority of these structures are in this magnitude or this size helps you tune your solution so that you can hit that size. And then the other ones become a variation on your base. And then the other part of it is just understanding your competition. So looking at the California market, 70% of the offices built in California are built using structural steel. And then, 28% are using concrete and a little bit on wood. Now, this survey was done before mass timber started kind of coming into the scene. So I'm thinking those are all like single story, low rise type office buildings is the wood construction. So most of them are using this type 1 construction, steel or concrete. And you realize real quick that in order to compete in this market, you're going to have to go toe to toe with steel construction and be able to compete in that market. So going out and talking to all these customers and just doing a bunch of research, a bunch of reading, you start to pick up on all these trends that are happening in the office market. You start picking up, and a lot of the recent trends are around sustainability, right? So you start picking up on trends like, comfort, all electric, healthy buildings, things like that, energy efficiency. You've got the, LEED, for instance, has been pushing energy efficiency for years. And now recently everybody's starting to transition to where they're really focusing on embodied carbon. So I feel like, energy is here and now, and embodied carbon is where we're going with these building materials. One of the things that became very, very clear early on, all the way through, is flexibility is king. Developers, owners, they all want a flexible building. They want to be able to retool it or, come in and do a tenant improvement with as little work as possible. So really zeroing in on these values was important. Going through this phase, and this took a little bit, but we've kind of watered it down to what our 4 primary drivers were, is that we needed to be flexible, we needed to be sustainable, we wanted a healthy building. And of course, this was really educated by, influenced by COVID. As we went through this whole COVID journey together, all of a sudden healthy buildings became very important to people. And I think they'll continue to be important to people. And of course, you can only build a building if it makes sense to build the building from a cost perspective. You're not going to build something that you can't make money on when you rent it. So cost is of the utmost importance. So whatever you come up with and you hit these things, you've got to be cost competitive in the market. If you're not, you really don't have anything. That you might have a niche market that you might be able to sell to 1 or 2 people. But if you're not able to be cost effective, you can't really realize the value of these other things. Okay, so then we went into this next phase. After we established that the market was sized, we thought we could compete in it, we thought it was big enough for us to make an investment in, we started in this, what I call this inception phase. So this was basically developing the initial concepts, soliciting feedback, more feedback from the market, and test fitting. So it was really cool because I was at basically this sales engineer at the time. So I would actually slip slides into my decks as I'm presenting to architects and different people, just to get a reaction from them, just to see what they said, see what they thought. It was kind of fun because I was doing this market research as part of my job, right? And part of my day job, I guess I should say. And through this whole process, updating and refining and updating a cost model and all these different things that go into it. So remember from before, we'd already identified, some of these key principles that we wanted to pay attention to. So, healthy and sustainable was kind of the top of the list. Flexibility was very important. Cost was very important. And we are trying to identify kind of this product. We don't know what it is yet, but it needs to be in that orange zone in the middle. It needs to be in that cross section between all 3, where it can meet all those demands. So started looking at different framing systems and started really zeroing in on, embodied carbon. Energy is more of a mechanical systems, operational efficiencies, insulation type thing. the thing I have control over as a structural precast provider is, at the time, thinking I have control over the concrete. I have control over the structure. So where do I start? How do I start zeroing in on this? And I started breaking down what a typical building was for me. And I started breaking it down by volume of concrete, because for me, concrete has a lot of embodied carbon in it. And the more I can reduce the amount of concrete, or the more I can reduce what's in the concrete, the bigger impact I could have on sustainability. So, I have two steps that I kind of go through as I'm thinking about this. And I'm thinking of this as really high level. I don't want to get into the details, because you get bogged down, and it prevents you from seeing the big picture if you dive too deep too quick. It slows you down. So big picture, I want to reduce the volume of concrete. That's going to be, my first and foremost. And then the second step is going to be reducing the quantities, or I should say, reducing the Portland cement in the concrete. And the second step is reducing the quantities of concrete and steel that we use in the actual construction of the building. And both of those come into play, and you can make some pretty big impacts with both. So the first thing to reducing your embodied carbon is to understand really where it's coming from, and also what you can do about it. So concrete itself isn't bad, right? If you think about it and you start identifying the sources of carbon in your concrete, it's not the rocks, it's not the water, it's not the sand. It's really the Portland cement. It's that manufactured gray powder that you put in concrete that binds it all together. And so when you look at the global warming potential of a yard of concrete, it steps out at you very quickly. And I was using a tool that ZGF made publicly available. ZGF LCA tool is actually a really handy little spreadsheet they put together. I use it all the time. I love it. But it quickly identifies, that cement is the biggest driving factor if you look at a yard of concrete. So if you look at it on the screen there on the left for normal weight concrete. And then what caught me off guard a little bit, and I never really thought about, was when you look at lightweight concrete, the lightweight aggregates actually have a pretty significant carbon footprint. And you're thinking, wow, they're just rocks that you dig out of the ground. Why such a carbon footprint? So I started digging a little bit, and I realized that they actually manufacture lightweight aggregates. You don't just mine them. They mine, shale or something like that, claystone. They crush it just like normal rocks, right? They throw them into a big kiln. They heat them up to about 1200 degrees Celsius, and they expand them. They go poof, right? And they get lighter. So that process takes a lot of energy. It ends up being a pretty significant contribution to the global warming potential of a yard of concrete. So for me, my thing is, now I want to avoid manufactured lightweight aggregates. Volcanic ones are okay, manufactured ones are bad. And I want to reduce as much cement as I can out of the mix. Those are my two goals. So how do the classical way to reduce cement from a mix is kind of the mainstream right now is SCMs, supplementary cementitious materials. These are typically either natural pozzolans or man-made pozzolans that come out of, burning coal or come out of the steel manufacturing industry. These things can be used to offset cement. Like you can put slag into a mix, and for pound, you put slag in, you can take cement out. So these are the types of things that we're able to do here and today. I know I feel like they're Band-Aids, and I know things like fly ash, because nobody's building any new coal power plants. That's a resource that's going to disappear, and we're not going to be able to use that in the future. I also know that, blast furnace slag, blast furnace steel production is very inefficient, and the world is slowly moving to an electric arc furnace. That resource is going to slowly go away. So there are future innovations. There are things people were working on that hopefully will solve this and come up with new and exciting ways to make concrete. And in fact, there's research that I've been seeing that has Portland cement-free concrete, like geopolymer concretes, things like that. That I think is going to be kind of in the next 10 years, you're going to see these technologies emerging and replacing traditional Portland cement concrete. Or the Portland cement industry is going to come up with a way to tune their Portland cement down in carbon footprint. So the next way to actually control this is not really with the mix, but how do we use that mix? So I have here an example of like a 30 by 30 building grid of different ways to build. So one of them is a cast in place two-way plate, post-tensioned slab. Typically, I used to see 8 inches. Often now I'm seeing 9 inches. just because the 8-inch one tends to deflect over time and things like that. So you tend to see it get a little thicker, up to 9 inches now. And to be honest, there's not a lot of real control. So even if you spec an 8-inch, you might get a 9-inch. Next one I'm looking at is a topped precast hollow core. And you think, oh, hollow core is great, right? It has a bunch of holes in it. It's got to be lighter. But the problem is you put this big topping slab on top of it and it makes it pretty thick. It actually is not, it's actually worse than the cast in place that you're trying to replace it with. And then this third section was one that we actually developed and optimized as we were going through and developing this. We went through and we came up with this roof floor plank and really optimizing the shape around minimizing the amount of concrete that we're using, minimizing the amount of early strength that we needed. We wanted to drive the early strength down because as you add these SCMs, these different materials, it slows the reaction of the chemical reaction down of the concrete. So the weaker you can make the concrete and at release, the better. Now there are some practical limits to that, but we took it down as low as we could. And this is the kind of the shape we ended up with. And you can see just by playing with shape and adding shape to the system, you can really tune the thickness of the concrete down. So you're losing a lot of concrete. And if you remember earlier where I had all those different tables, the floor system was somewhere around 30% of the concrete on the job. So really paying attention to that floor system makes a big difference. Okay, so then going with that, as we started looking at reducing carbon, remember it had high impact potential, 35% of the structural concrete, so I was off a little bit earlier. We set some goals. We wanted to do a 70% replacement. This is done in the industry and foundations and things that have months to cure. They can do that and make it work. We wanted to do that in a manufacturing environment where we could get 3,500 PSI overnight. So that's a bit of a challenge, but we were able to overcome that. And then we wanted the slabs to actually be thinner than the slabs that are used in steel construction. In other words, we want our slabs to use less concrete than the slabs in steel, which is kind of an anomaly too. So we came up with a bunch of initiatives to do this. We leveraged the shape to reduce the concrete and the reinforcing. We used a pre-top system. So remember I was saying like the hollow core is not the problem. It was the topping slab. It was that added layer of concrete that you put in the field to tie it all together. So there are technologies or methods that you can eliminate that and tie it together in different fashions. So we really went down that road, really just to reduce the amount of concrete that we're using on a job. And then we went and did our own fire testing on our system. The building code requires a 5-inch thick slab for a minimum 2-hour fire rating. We wanted to go 4.5 because that's all we needed for strength. And so we went through and we actually fire tested a 4.5-inch slab with a slightly different mix to make it work. And we were able to achieve our 2-hour fire rating with a 1/2 inch less concrete than normally would be required. And then in order to get that 3,500 PSI overnight, we overcame that with heat. So by heating the forms, we were able to get that 70% replacement in, I think it was like 15 hours, something like that, where we could turn our forms every day and still achieve that high cement replacement, really dropping the global warming potential of our mixes. And you say, well, that's kind of cheating, right? You're using electricity to heat your forms. That has a global warming impact, and it does. But I would say I'm able to cut about 110 kilograms of CO2 per yard at a cost of about 12 kilograms of CO2 per yard if I take it off the grid. And if we are using our solar, our on-site solar to do that, then that value drops even more. So there's a lot to be said for that, I think. So overall impacts, just to give you an idea of the magnitude, when we take all this together and we apply that same strategy that I just applied to the floors and we apply it to all the different elements on the building, again, very high level thinking here. We're not going into the weeds. We're just trying to put the system together. We're able to get 23% less concrete in our structure over a cast in place, and roughly, a little bit less, not quite as good over a topped precast. But then we're able to get also 47% less CO2 in our mix on average across all of the products. And when we put those things together, we get about 60% of the CO2 is being removed from our concrete mix, which translates to about 46 kilograms per square meter in our study, which is, most buildings are going to come in around 220, somewhere in there, an efficient building. So you're losing about 20% of the CO2 from the concrete all by itself, just the concrete, not talking about the steel or anything else. So these are the kind of things that when you have the time to go through it and productize it, you can make a really big impact, and you end up building things maybe a little bit different than you would have otherwise. So the next thing that was a really big deal talking to owners was this flexibility. So always asking owners, hey, what do you like about the steel? What do you like about the cast in place? Always kind of picking their brains whenever I'm in a meeting with them. You know, what they liked is they liked the mild reinforced slabs in the steel building. They liked how easy they were. They could drill holes in them. They didn't worry about it. They liked that the beam spacing was 10 feet apart so that they could fit stairs in between them and things like that. If they wanted to in the future, cut a stair opening. Really, the key was they wanted something that was easy to modify. Ask them what they don't like, right? They don't like the high floor to floor heights that are required for steel because you have all this steel underneath the floor. They have a less attractive soffit. They've got the insulation. They've got a bunch of stuff hanging under the slabs. And then also floor vibration can sometimes become an issue with steel construction if it's pushed too far. Same thing about concrete. Concrete cast in place buildings, people like the low floor to floor heights. They can usually compress their floor to floor heights, get more floors per under their building height. They like the flat soffit. They like that they can expose that soffit. They can paint it or something and look up at it, and it looks nice. What they don't like is they don't like the flexibility of a cast in place system. The post tensioning in the decks is a real problem for them. They're always afraid they're going to hit one of the tendons. It's going to go flying out of the building. They find that they're difficult to modify and difficult to go in and strengthen after they modify them. So taking this kind of input is really important because this kind of drove us to how we developed our system. So I was showing you a little bit about that rib plank system that we developed. In a sense, we were trying to mimic a steel system using concrete. So we put our beams at 10 feet on center, just like steel, really thin slab, mild reinforced slab that could be Swiss cheese, just like steel. We actually made a conscious effort to overstrength the slab so that if you did make future penetrations up to about 2 feet, you wouldn't have to do any kind of supplemental support of the system, that you could just go in and make that modification. And it wouldn't require structural engineering to do it. So these are the type of things that we built into it. We also, if you notice, we put that mechanical notch in there. That is an effort to tuck the ductwork up into the structure and allow us to lower the floor to floor height without impacting the performance of the system itself. So these are as we start looking at products, these are the type of things we're looking at, and you wouldn't never do these on a project because all of these little details are extremely difficult and take time to work through, and you usually don't have that kind of schedule on a project. So shifting a little bit now, before I jump into cost, because I remember I said cost was a really big deal. And I want to just, as we think about this, a few basics for offsite fabrication. So I think a lot of people have seen this before. This comes from, McKinsey, basically talking about manufacturing versus construction and about the efficiency, the $1,000 per worker that's generated in manufacturing versus construction. And it shows that construction has remained kind of static over time. In fact, they've gotten less productive over time, whereas manufacturing, like auto manufacturing, has got more productive over time, right? So the more we can move out of the field and into a manufacturing environment, the more that makes sense, right? But as we look at this industrialized construction, I'll say volume does matter. So if we're taking a construction project and we're taking a slice of the pie of that construction project and we're moving it off site, part of that's going to be material, part of that's going to be labor of your field scope and then you're replacing it with this prefabricated equivalent manufactured element, right? Well, with that, you've got usually more efficient with material, more efficient with labor, but then you've got these two added layers. You add in the engineering and logistics layers, so the trucking and the engineering that's required to deliver these to the project. In order for it to make sense, you have to kind of take all four of those things and squeeze them into the same cost model as the two things you're removing. So if you don't have enough scope that you're moving off site, if you don't have a large enough magnitude, then all of a sudden the offsite manufacturing doesn't necessarily make sense financially. It may make sense for other reasons, for schedule or this or that. But if you can increase the scope, so let's say, for us, we deliver the structure. Say we're struggling to have enough scope in the structure to really achieve what we want to achieve and incorporate the engineering and logistics, then grabbing adjacent scopes or other things and integrating them into our product is a great way to increase the amount of scope that we're delivering so that we can we can deliver very cost effectively to the job site. So, think about that. How the more we can deliver on a truck and the more we can deliver with the logistics, the more value it brings to the project and the more affordable it becomes. Okay, so when we're looking at adjacent scopes, there's a couple big ones out there, right? The structure is a big one. Of course, that's the one that is kind of our base. Facade is a big one. We've actually done this in the past where we kind of integrated structure and facade into one element and bring it out to the job site. I will say that the struggle with that is it becomes very custom and very difficult to deliver, and it requires a pretty top-notch engineer to kind of stay with it. And you usually end up pissing off the architect because they don't get exactly what they want because you're trying to balance a structural system with an architectural system. I've done that for a while. It never really worked out. But I found that this mechanical was a great way to incorporate what we're doing and deliver it to the job site and really add a lot of value. And what's interesting is, people think of radiant systems as being this premium system, very expensive, delivering that to the market when it's constructed out in the field. When we do this in the manufacturing plant, we can drive the cost down considerably. So in fact, so much so that I believe that I can deliver a radiant solution to the job at a lower price than a conventional system can be delivered to the job. It's pretty crazy. So people are getting this premium. It's kind of like you're getting this premium concrete system and this premium radiant system. You put them together and you get both of the benefits of those, but you get them at a reduced cost. So it's kind of a cool way of looking at it. Haven't really dug too much into the plumbing and the electrical. There's a lot going on there. That's a lot of effort. So we jumped in with basically increasing the scope of our product by incorporating structure and mechanical as one in our product. And I'll show you a little bit. I just want to kind of give you an overview of the system configuration that through this iterative process took. So looking at a typical office building, you typically have a core area where you've got the bathrooms, the elevators, mechanical rooms, things like that, electrical rooms. So we kept that very simple, very traditional kind of delivery on the mechanical system there. But in the main part of the building, we have all of our prefabricated rib floor planks, and we have all of that is thermally active deck with radiant heating and cooling already incorporated into the system. And then working with our mechanical partners, we came up with concepts of how this whole system works, how you can have the radiant heating and cooling with basically putting the whole system together, using ceiling fans to make the space more robust for comfort, using solar control to minimize the amount of heat that comes in the windows and heats up that space so that you can really eliminate a lot of the mechanical systems. And most of what you're doing is just supplying fresh air into the space. And then your space heating and cooling is taken by the radiant. I talk about a product, going through and iterating on that product. There was a lot of iteration that went into this. I mean, we started out with a very simple single zone panel. As we got into it, we realized that taking care of the edge was important and it had to have its own zone. So we split it into a 2-zone panel. As we got into it, we realized that we had to have independent controls for multiple zones within the panel, not just within the panel, but within the building. So we started incorporating more scope on the panel, incorporating all of the hydronic piping that goes into the building, as well as all the controls, sensors, everything that's needed to run this panel. We ended up merging and incorporating into the panel so that we could deliver this as a true product to the job site. And again, the more of this scope we can incorporate, the more affordable it becomes to deliver and the faster it is to install it in the field. And then, with a nod to that adaptability, remember I mentioned that was really important. So not only being able to cut openings in the slab, that's part of it, but the other part of it is that, thinking about simplifying tenant improvements by installing that radiant and keeping it fixed and it never changes. That's one less system that has to move whenever you do a tenant improvement. So you're not moving, You're still moving the air ducts if you need to, but you don't have all the reheat piping or any of that other stuff that normally goes into a tenant improvement. It just significantly simplifies that process. And then it also, if you think about the level of control, most radiant buildings are built in a way that they only have very few zones on a floor, maybe 4 to 6 zones on a floor. The way that we're panelizing the system, it allowed us to really give this microzoning approach to the floor. Each one of these microzones has its own learning curve. It basically studies the space, studies the comfort band, and then targets a new temperature the next day. So it's always constantly learning from the previous day and targeting the new temperature, idealizing a comfort band. If somebody in the space or if people are consistently uncomfortable, then you just change the band, the target band, and then it constantly targets that new comfort band. So, and if you have different requirements in different spaces, then this microzoning approach allows the building to learn those spaces independently. So it's really a pretty interesting system. I think it took us about a year to kind of come up with all these concepts. And then, this whole time, like I said, I was going out to the market, I'm talking to architects, I'm talking to developers, talking to all these different people. And the idea is that we're basically marketing this to the market. We're giving a presentation, we're showing them the system, we're taking their feedback, we're processing it, we're improving the system. And then next time I go out and talk to an architect or a developer, I have this new improved version with a new messaging, and we just keep iterating on it. So it's the very agile process. We're iterating, but we're doing this with the system, with the marketing of the system. We haven't actually built anything yet at this phase, right? We're just going out there and soliciting feedback and kind of steering the system into what we think the market's going to accept. And then, so this was really that phase. The gist of it, right, is really developing the system and making it something that the market could accept. Then once we got this done, the next phase was actually what I call the iteration. This is where we're developing the detailed system. And this is another iterative feedback loop, but instead of going to the market in this feedback loop, we're going to our internal customer, which is our manufacturing teams, our field teams, things like that, the people that actually have to build this. So we've kind of set the direction by going to the market. Now we're going to go to our internal teams to really get into the details and build out how to make this the most efficient thing that we can, how to drive as much cost out, how to drive as much material out of the system as we can as we go through these things. So in order to do that, we set up a team, and now all of a sudden things are getting real, right? Now we need more people, bigger teams to get involved. We're starting to engage more people on the internally, engineers, project management, manufacturing teams, and we're really getting in. We're starting to spend some real money now, right? So the way we organized this in basically 2 teams because we set up a development team on the right. Development team is basically like a scrum. We meet daily. And we push through all these different elements. We have these SMEs, these are subject matter experts. These are people that are not on our team that we need to help us perform the work. So these are like our design engineers that we need to do the actual detailed design of the elements. People like that. This is our manufacturing team, our field team. These are the subject matter experts that we're pulling in and working with us. It's a little bit challenging because they are also pulled on projects. And so you're working with them for a while and they go, oh, I got a project, I'll see you in 2 months, right? But, we try to have enough work going that we can, compensate for that, because we need to, especially our engineers, right? They're going to be the engineer record on the gravity systems that we are doing. They have to own that. We can't own it. They have to own that. So, and then we have stakeholders, and these are all the different people that are going to be impacted by what we're doing. Our internal project management teams, engineering, calculations, our general contracting team, architecture teams, sales, marketing, all the different people that are influenced by what we're developing. Once a month, we report out to them, we show them all the progress, everything we've done to date, and give them a chance to give us feedback on the direction that we're going and what their thoughts, whatever they are. So then we have this other team on the left, and this is basically because this development team supports 3 roles. It supports our parking division, it supports our office division, and it supports our sales and marketing, our sales group. So whenever we're going after a pursuit, if they need a little more horsepower on it, they engage our group. So this group over here then we basically set the priority of the work. So we go through and we identify which items we'll be working on for the next week. We put those in a list, we feed those over to the product team, and the product team organizes around those tasks and accomplishes them. As we get into this productization process, we found that we really had a couple loops going. So we had these concepts that we're developing that are real high level that we got from our market research and our just iteratively going through the market. And then we come into this weekly component design philosophy meeting where we're meeting with a group of a bunch of engineers. So you can imagine you get 3 or 4 engineers in a room and you get 3 or 4 opinions. So some heated discussions, but it's good to get them out in the open. And then we go through and from that meeting, we have engineering tasks that go in the blue loop, and they do a component design, and there's a shape review, and then it comes back into that weekly component meeting. And then on the orange loop, we're taking stuff out of there, things that have been engineered, and we're taking them through and we're doing a 3D model of them. We're pricing them and getting vendor feedback on all the different components of them. We're taking them into manufacturing for review. What do you guys think of them? Can you do some time studies on them? Do you like what you're seeing? And then we take them to the field and we say, hey, what do you think about what we're developing? Take all that input and we come back to the weekly component meeting, and then we adjust. And that might generate additional engineering, say, hey, they really want you to change this. So the engineering goes and looks at that next week. And we keep iterating on it until everybody's happy. And once everybody's happy, then it kicks out of that process and it goes to our stakeholder review. And then from there, we start doing the detailed documentation and we start creating a standard. And then that standard goes to our project management group where they basically own it and implement it. So where to focus is very important, right? You don't want to give everything equal effort. So understanding where the impacts are. So, first I did cost by category. I look at, where are costs, and, obviously we have a lot of cost in materials, a lot of cost in our manufacturing labor, a lot of cost in our field labor. So that, looking at these different things, who has a big stake in this, right? Understanding that gives us, where we want to focus. Like, should we focus on engineering to minimize materials? Should we focus on manufacturing labor? All those different things. And then we also look at by component, so cost by component. So we look at the floor system, as you can see, is dominant. So if we're going to focus on any one thing, we want to really get the floor system right. And we've spent a ton of time on the floor system, right? And then you look at the beams, the columns, the lateral system are all kind of split equally around the other half of that circle. So we probably won't give those as much attention as we gave the floor system. Things like beams and columns, we're trying to give a lot of attention because we think there's a lot of advantages there. Lateral system, we're kind of kicking the can down the road because there's a lot of uniqueness about where you are in California and what the lateral system is going to look like. So I'll give you an example of some of the studies that we do. Coming down to that floor system, we started, digging into the detail, right? Pricing every little piece and component, looking at different options. So here we're considering a wire mesh option for the slab versus a mild reinforced option versus a mild reinforced option with integrated hairpins on it. And we went through and we did a cost study on all of them. We took it back to the manufacturing group. What do you guys think of this? They liked the price on the one on the right. They said, that's kind of unbuildable. The tolerances aren't there. We need something better. And so what we finally ended up with was a variation of that. It actually had the same number of pieces, but half the number of ties, which production liked. So it saved them labor in the plant. Using 2 individual bars overlapping each other rather than one solid bar with a hairpin on each end. And that solved our tolerance issue and gave them what they wanted for manufacturing. Then we did the same thing.
We're at time, but maybe like 4 more minutes.
Okay, I'll buzz. I'm almost done.
Okay.
So we did the same thing with our rib floor plank, just iterating on all these different things, coming up with more efficient ways to build the different various end plates. Same thing with our radiant system. You can see that we started very crude on the upper right or upper left, and we moved around until we have a fairly sophisticated system on the lower left. A lot of time on how we actually loop the radiant, how we route it in the panel to make sure that it's going to perform as we want it to perform. And then we released this. We sent it to the manufacturer or to our project management group, like I said. And out of this, we actually hired a group to do an independent study for us and discuss, what the energy efficiencies of our building was using the system. And as you can see, we're doing pretty amazing with an EUI down under 20 on this. Whereas if you go to the carbon tool, it looks like about a 93 would have been the baseline in this building at this region. So we're taking pretty massive savings in energy because of the radiant system. And then we did also a whole life carbon analysis on the system. And you can see that we have a 40% reduction of carbon over the life of the building compared to a baseline steel building with a VRF system. And anyway, that's all I have. I hope you guys enjoyed that. Sorry to go a little bit fast. I had a lot of material to cover. Anyway, if you have any questions, please shoot.
Great. Yeah. Just maybe put them in the chat. We'll just go off mute. But that is very cool. Thank you for sharing, John. At least for me, who's not in this industry, just seeing like the iterative and incremental approach to figuring things out, and it's.
Yeah, what lessons learned, John, that you can share the last 2 weeks? Like,
What's that?
do you have any lessons learned you can share?
I think one of the biggest challenges is we probably underestimated how our market acceptance, going to a general contractor, a lot of times we're a subcontractor, and going to them and saying, hey, we've got this integrated solution, and they've already got their own mechanical engineer on the job. And they say, great, we want your integrated solution, but we don't want the radiant. So take the radiant out, we want the rest of it. And trying to explain to them, well, it only works with the radiant. You either get the radiant or you don't. and they're so used to doing these custom solutions that it's really hard to sell them a productized approach. They're always trying to change it on us.
Right. You got to be part of the solution so that you can unlock value right from the beginning.
Yeah.
I've got a general question, John. Are you seeing, like, for large industrial markets where floor flatness is like a big deal, like warehouses or industrial space, are you guys seeing an uptick with all the data center work and looking at those new solutions like you presented here with the thinner floor slabs?
So this is targeting commercial office.
Okay.
So we're not targeting warehouse or data center. We stayed away from those. We don't have a lot of data centers in California, ironically. And floor flatness is actually a huge concern because we're doing that pre-topped solution where we've got little pore strips in there. Keeping those things level and even is very important. Otherwise, you have to go through and do a leveling compound on top. So we've actually spent a considerable amount of time on floor flatness on these, to where we purchased automated finishing equipment. We've tuned our pre-stressing operations so that the floors are fairly flat, very little camber from the beginning, so that we don't have, the less camber you have, the less differential camber you have, and the less differential camber you have, then the more consistent your floor and flatness is.